All right, hello everyone. Welcome to the second week of Aggregates. Last week we covered 5 tests, and this week we are covering 4 more tests to make it to a total of 9 tests conducted for Aggregates. This is the longest lab with the multiple number of tests that we're running. This is going to be your longest report that you're writing, but it's not too hard. It's straightforward as long as you understand the tests. So we'll cover flat and elongated, fracture faces, uncompacted voids, and sand equivalency or clay content. So we'll go ahead and jump in week 2. So flat and elongated, the ASTM is D4791, if you ever want to look that up. And it's called the standard test method for flat particles, elongated particles, or flat and elongated particles in coarse aggregate. And these flat and elongated particles, they will interfere with construction and consolidation. So it's always important to do a quick aggregate test to see what percentage of flat and elongated particles there are. So the test equipment that you use, you'll use a balance like normal and a proportional caliper device, which is that blurry image on the right. We'll see that a little bit better in the video, but what you can do, that little black knob fits into a calibrated hole, and you can see there's 3 more to the right of it a little bit, and those allow you to change the ratio at which each of the 2 openings are. So the opening on the left right here, this is for testing the lengthwise of the aggregate, and this is for testing the width. So you put the longest piece right here, and this would swing shut until the aggregate fits against it. So if it's a long piece, it'd stick out way further. And then what happens is this piece comes in close, and you can set it to a 2-to-1 ratio, 3-to-1, 4, or 5. And so wherever that pin sits, if the length is 5 times as big as the width, I mean, some specifications will ask you to do 3-to-1, some will do 5-to-1. In our data, we are providing you with a 3-to-1 ratio, so you can mention that in your report when you talk about the methodology on the flat and elongated test. You always want to do it on large aggregate. There's no point in doing it on small aggregate because you're not going to be able to, I mean, it's not going to be worth it to test that. So you always test it on 3/8 inch material or larger, and you want a 1,000 gram sample. You don't want to test 10 pieces or 10 aggregate, like 10 rocks, because that's not going to be a good sample for actually what you're putting out in the field. You want a big enough sample to where it's going to give you really proportionally what you have and how much is flat and elongated. The procedure is very similar to the other ones. You want to oven dry your aggregate, make sure it's not filled with water. It's easiest if you oven dry it prior to doing testing, and then you can weigh it, and that way if you do a weight ratio, let's say you have 100 grams that passes through that's flat and elongated and 900 grams that doesn't, you don't want water to be in some of the aggregate and not in some of the others, so it lets you use the true weight of the aggregate. Again, you sieve the material and retain it above the 3/8 inch sieve. You set the caliper device to 3-to-1 proportionally for what we did in the lab. And you can, what you'll do is you'll test the aggregate to see if it passes the caliper using that little device. And then you make 2 piles. You make a flat and elongated pile and a not flat and elongated pile for each of the for each sieve. So you do it in 3 sieves technically. So you do a 3/8 inch sieve, you do a 1/2 inch sieve, and a 3/4 inch sieve. You have 3 different like aggregate sizes, and of like, let's say you do limestone, you would have a 3/8 limestone, a 1/2 inch limestone, and a 3/4 inch limestone. Because some of the flat and elongated particles might be in that larger aggregate size and not in the smaller one. It's always good to look at that. So you'll make 6 piles technically when you do it, and then you can calculate percentages by mass. Very easy. Here's just a look at what the device looks at a little bit easier. So up in the top left, we're showing that what you're checking is the maximum length compared to the minimum width. So like this aggregate right here, that one is pretty long. You can't really tell. It's probably pretty thin though. So this one, you would put the long end here, and it would close this little opening and see if you can slip it through sideways. And if it does, then that technically is flat and elongated with the 1:5 ratio. And so there's different aggregates you test. If it doesn't pass through here, then it's not flat and elongated. So it's very simple. You can see him passing through an aggregate. This one technically would be flat and elongated here. And then we got a video of Jason at NCAT doing this test. He does the test with a 1:5 ratio. Remember that we did 1:3.
Flat and elongated particles for coarse aggregate is ASTM D4791. This is a simple test to run, and as you see here, this is our flat and elongated apparatus. So you may be wondering to yourself, why do we care why we have flat and elongated particles in our pavement? Well, this is a flat and elongated particle, and if you think about it and look at it, these tend to be very brittle and break real easily once they're put into pavements. So that's why we do not want them in our pavements, because they then will not stand up and last. If they make it through an asphalt plant, they'll probably get broken by the roller, or they may even also get broken up while they're going through the plant. So that's why we run this test, to make sure we do not have a lot of these particles in our pavement mixes. So the apparatus, you can run at different ratios. It's a 2:1 ratio, a 3:1 ratio, or 5:1 ratio. Depending on the agency, depends on the ratio that they use. What I'm going to demonstrate here is an apparatus set up at a 5:1 ratio. And the way you change the ratio is just take the screw out and put it in the ratio you need to test. But as you can see, this one's set to run a 5:1 ratio. Test is easy to run. You take one of your particles, put it in lengthways, and line it up, and that's your length. And then you flip your particle over on its side to see the thickness. And if it passes through, like this one does here, we consider this flat and elongated. And I would make a pile for flat and elongated. Same way with this particle here. Put it in lengthways, turn it sideways to its thickness. If it slides through, then it's considered flat and elongated. As you see this particle here, again, length. And as we see, this one does not pass through, so that would be considered non-flat and elongated. And that's what we tend to look for. We want particles that are not flat and elongated, because they tend to be stronger and more durable particles.
So a very simple test. It does take the most amount of time in the lab, but it's very necessary to do to see if you have too many of these particles. So you can see these are kind of rounded particles. This is what you want in a mix. These are actually flat and possibly elongated, but these right here are elongated particles. What we test is for flat and elongated particles, so they need to both be flat and elongated. There's in that specification, you can test for just elongation or just the flatness, but that's not what we do in this. That's why it's called standard test method for flat particles, elongated particles, and flat and elongated particles. So that's that test. The second one is the fractured faces. ASTM D5821, standard test method for determining the percentage of fractured particles in coarse aggregate. So when particles that are fractured probably come from a quarry where they're blasted or broken up by a crusher at a quarry. And so that angularity provides stability in concrete slabs and granular bases, asphalt pavements, etc. If you have river gravel, you think about that. It's a very smooth aggregate because it's been brushed over by water and sand a lot in streams, and that wouldn't provide a good interlocking face for granular bases. So any aggregate that has got those fractured faces on it, that's what you want. Again, this is a really blurry picture. I've got a few more pictures to show y'all, but just for this test, you want a balance again. You want sieves to get their right aggregate size for testing, and a splitter that's listed in the specification. Y'all wouldn't have used the splitter, but we use it to split the material out into a good size without messing up the sample. If you scoop from the top of a sample, it can mess up your test overall, because you might be getting stuff that's segregated from the other bits. And we'll show you more of that when we get into asphalt. But splitting just gets you from a sample that's maybe 5,000 grams all the way down to, it would get you from 5,000 to 2,500, 2,500 to 1,250, and so on. You can you'll work your way down until you get a good proportional size. So you only need 700 grams roughly of aggregate sieved. So here is a quick picture. You can see this is river gravel most likely, and there are 0 faces of it that are crushed. And you can tell by you can tell that it's crushed when a part of the face is got like really rough edges to it. I think it's 25% of one face has to have that crushed look. So you can see this bottom right one. It's got that one face crushed right here, and the rest of it is round. So that would be considered a one crushed face, or one fractured face particle. This one up here looks like 1, and then on the bottom it looks like it's laying flat. So it could be 2, but you categorize them in either 0 fractured faces, 1 fractured face, or 2 fractured face, and then you do calculations based on that to figure out what your percentages of fractured faces. And specifications ask you to have different percentages for that. Sometimes it's 80%, 90% fractured faces. This is always an important test to do as well. I know it says two or more fractured faces up here. I can't tell. My assumption was that this one was 1, but I didn't see it in person. So the procedure: you want to sieve the coarse aggregate out. You want to keep all that coarse aggregate. You don't want to do this test on smaller stuff. Then you wash and oven dry it again to remove moisture. You'll count the fractured faces on each piece of the aggregate. Fractured face is more than 25% of the aspect ratio or face is broken. So on one face, if 25% of it is broken, then you can consider it fractured. If it's just a small, tiny nick that's on it, you don't really want to count that. And then you separate it into piles of 0, 1, or 2 plus. So it can have more than 2 faces that are fractured, but we don't want to do any additional piles. And then you calculate the percentages of 1 or more fractured faces and 2 or more. And I'll show you that later when we look at the data. So here's a video on doing that. It's very simple, same as flat and elongated, but you're having to touch every single aggregate and look at it and just do your best guess at if you think it's a fractured face, and how many.
When it comes to coarse aggregate particles, we want to have particles that are crushed and angular. Those particles tend to interlock very well and will provide us a stronger pavement when they're used in our asphalt mixtures. The way we determine how our fractured or angular particles are of our coarse aggregates is called fracture face count, and it's ASTM D5821. This is an easy test to do. Really, all you have to do is look at your aggregate particles, determine if they have 2 or more fracture faces, 1 fractured face, or no fracture faces. And we'll take our particles, we'll divide them in those 3 piles, and then we'll weigh each pile and determine the percentage by weight of our total sample. Or you can also do it by particle count, where you would get 100 particles of the coarse aggregate that you're testing, and then divide them into 3 piles and count the number of particles you have with 2 or more fracture faces, 1 fracture face, or no fracture faces. So I have my coarse aggregate here that I want to test, and you just pick up the particles and look at them individually. So with this particle here, we can see that this side is rounded, but if you look on the other side, you can see where it's been fractured, where it went through a crusher. For this particle here, we will label it as just one fractured face, because you got one fractured face on one side and then it's rounded on the other side. The next particle you see is rounded and smooth on one side, but then as you turn the particle around, we have a fractured face on this surface, a fractured face on this, and another fractured face on this side. So we would label this as 2 or more fractured faces. And I would make a pile for each one. This particle here, again, rounded on one side. We have a fractured face on this side and another fractured face, so 2 or more. The aggregate particle we see here, you see it's just rounded on all sides, hasn't been through a crusher or didn't get crushed as it went through the crusher, so that would be no fractured faces. Same way with the particle here, smooth on all sides, so no fractured faces. Because what we're looking for our particles to have fractured faces. And it's good if they can have 2 or more fractured faces. The way specifications tend to read most of the time when it comes to fractured faces, it depends on where in your pavement layers you're going to be using this aggregate material. So if you're using this aggregate in the surface, the specification may call for 95% 2 or more fractured faces, or 100% 2 or more fractured faces. So we're looking for these fractured faces in our coarse aggregates. Again, with this one, there's a fractured face on this side, and this side, so 2 or more. Then we would just take all our particles and go through them. It takes a little while to do this test, but it's not a difficult test to run. We can see this particle, one fractured face, and smooth on this side, so that'd be one fractured face. And as I stated earlier, the specifications read depends on where in your pavement layer you're going to use material. It may say you have to have 95% 2 or more fractured faces, or it may read that you have to have 90% 2 or more fractured faces and 95% 1 or more fractured faces. And once we have all our particles in their separate piles, we would either do the calculation by weighing each pile, divided by the total weight to get the percentage, or do it by particle count, where we'd get approximately 100 particles, divide them into their piles, and count out the number from each pile to determine what percentage out of those 100 particles is 2 or more fractured faces, 1 fractured face, or no fractured faces.
All right, so you can see, pretty simple test. The next one we do is Uncompacted Voids, ASTM C1252-03. The -03 is the year that it came out, or has last been revised. So it's been 17 years since, but it's a pretty easy test to do. There's not much to change on it, maybe different apparatus stuff, but so it's called the standard test method for determining the uncompacted void content of fine aggregate. It helps you determine water demand and if hydraulic cement is being made. It also makes an impact on the flowability, pumpability, and workability factors of the aggregate in concrete. So the equipment that you have a cylindrical measure, that little brass looking thing down here. You have a funnel and stand. It's just a mason jar upside down with a funnel on the bottom of it. You have a glass plate, or you can just use a pan. Actually, it says pan here. The glass plate, I believe, is this piece here that's sitting on the structure of that. And then you have a scale. And then you can use a brush, spatula if you need to. The sampling procedure, you just need 600 grams of aggregate, just enough to fill the cylinder and over it. And then the procedure, the thing to note is that you run it twice with the same material. It's a very easy test to do, and you want to run it twice just so you get the right value for it. So you mix the samples until they're homogenized. You place a finger over the hole in the funnel and pour the material into the funnel or the mason jar. That way the material doesn't fall out of the bottom of it until you're actually ready. You want to level the material in the funnel with you can use a spatula, you can use your finger, you can do whatever. And then you remove your finger, let the material fall into that cylindrical measure. And once the funnel is empty and the cylinder has completely overflowed, you scrape off the excess of the material off the cylinder. You don't want to shake it. If you do shake it, what's going to happen, so you're going to have a little mound on top. And if you shake this, what's going to happen is you're trying to test the uncompacted voids of it. If you shake it, you're going to move some of those particles and let them settle down more, settle down better than they would naturally. That's why we want to fill this up, remove our finger, and let the test run and just fill up this cylinder completely. Once that's done, you carefully scrape off the top, and then you move it to the scale. What you can do is once you scrape off the top, you have the complete volume filled with aggregate. You can actually tap it on the side a little bit to let it sink, so it's not going to, no aggregate will fall off the top, and you'll see me do that in the video. And then you determine the mass of the cylinder to 0.1 grams and calculate the uncompacted voids. So I did a video for this, and it's not too long. Go ahead and watch it.
And now we're going to test the uncompacted voids of fine aggregate. We've got gravel and we have sand here. And the procedure for this is we have this contraption right here for testing the uncompacted voids. And we have a cylinder here that sits right underneath this mason jar. We'll fill the material in the top, and then you want to release it, let the material fall in and compact itself. You don't want to compact it with any tamping like we've done in all the other tests. So what we'll do is we'll scrape off the top and we'll go weigh this afterwards. So I'll go ahead and do gravel first. I want to weigh this thing first. $185.1. So I'll record that value, and then you place it in there. This is the hardest part when you're by yourself, is dumping this material with your finger plug in the hole. That wasn't too bad. Alright, and then we want to level the material so that it comes out uniformly out of the mason jar. And then make sure it's there, and then I'll move my finger and let it fall until it overflows. There we go. So now we want to see what the volume, what the weight is of the material that's in the volume of the cylinder. So we need to scrape off the top. So carefully scrape off that material. Try not to shake the cylinder at all, because then it'll settle and get more material than you're supposed to. So now that we have that total volume that's in there, what I want to do to safely move it over there without tipping any is I can hit it a few times to lower it down. It's going to be the same weight. 324.5. And so then what we would want to do is redo this test one more time. We want to do it 2 times total with the same material and get that same weight, but we won't do that for this video's content.
So pretty simple test. I guess the one thing I could have done a little bit better is brushed off that bottom rim, because it looks like there might be a little sand there. Possibly not, but I should have checked that just in case. And then the last one is the sand equivalency test, ASTM D2419, standard test method for sand equivalent value of soils and fine aggregate. So this test determines the amount of fineness and characterizes the clay materials present in the aggregate source. Basically, the question of this test is, how dirty is this sand, or how dirty is this fine aggregate? You'll see when you're trying to determine the character of the clay material, you're just trying to see if there's clay in it and what percent of maybe even deleterious material, if there's any vegetation in it or organic matter that's in it that shouldn't be. You can figure that out with this test. The equipment that you need, there's a lot more equipment. Some of this is just that's sitting in the lab that you use. You have a graduated cylinder. You use a rubber stopper on the top. There's an irrigator tube where you fill in a flocculating solution. There's a weighted foot assembly for the very end. You use a siphon to get the material into the flocculating solution in using that irrigator tube. You'll see it. There's a measuring tin. The measuring tin is an 85 millimeter tin that you use. And then you want material that's passing that 4.75 millimeter sieve. And then you have a funnel as well to put your material in. You have a timer because you have to wait a bit, and you can use a mechanical shaker. In the lab, we've never used one. We always just shake the material according to the specification. But in the video that Jason has for us, he actually uses a mechanical shaker and actually had never seen it until this video. So that's pretty neat. The sampling technique, you want at least 1,500 grams passing the number 4 sieve for sampling to occur. And then you scoop that amount in that little measuring tin, which is an 85 millimeter tin. Procedure, siphon 4 inches of that calcium chloride flocculating solution into the graduated cylinder. Then you funnel the test specimen that you have from that measuring tin into the cylinder. You want to tap the cylinder at the top to release the air from the sample itself. And then you let the specimen stand for 10 minutes so that that solution can work its way into the material and try and get those clay particles to kind of stick together. Then you put a stopper on the cylinder, you partially invert it, and then shake to loosen the material. The shaking, what you do, it's called a throw. I won't get into it a whole lot, but you want to shake it for like 60 seconds, 100 times, or use that mechanical shaker. So you shake it 60 seconds. You flush the fine materials into suspension by irrigating the material into the cylinder, or irrigating the material into the cylinder. You'll see how this has worked. It sounds kind of weird, but we'll see it in the video, and Jason explains it really well. Then you fill the cylinder up to the 15 inches with the solution. So you want to fill it up all the way now. It was at 4 inches, now it's at 15. Then you let the material sit for 20 minutes. And then you read and record the level of the clay suspension, and then you use that weighted foot to get another, so lower the weighted foot assembly into the cylinder, subtract 10 inches from it. You don't know why, but you'll see why and understand it. And you get a sand reading. And then you calculate your sand equivalency value to the next highest number if it's a decimal. I have a few images for y'all just to make it make sense. So you've got your graduated cylinder, and then you have your aggregate. This is after you do the entire test. So after you do the test, you're going to have your sediment, which is your sand or any fine aggregate that you want to test. And then you're going to have suspended clay that's not sitting on top of that, and then flocculating solution that hopefully will not have any suspended clay in it at all. You want it all to sit down. And then what you want to do is you'll get a clay reading from the top of the clay, and then you use a foot, and the foot comes down, and when you can sometimes look at it and say, hey, here's the top of the sand or top of the fine aggregate. But sometimes it's hidden because the clay particles can work themselves into it. So you use a weighted foot that has a flat bottom to it. You lower it down and it sits right on top of the sand. When you do that, the clay kicks up into the air and up into this solution, and you can't see that line anymore. So it has a piece that's 10 inches above it that shows you if it reads 14.5 inches, you know that the actual reading here is 4.5. So it's just a really easier way to do it. It's used to estimate the relative proportions of sand and clay-like particles or plastic fines and dust. Again, here's that thing. You do your sand reading right here, clay reading right here. Obviously, you do your clay reading first, put that foot in, get your sand reading. And here's that equation for it. It's also in the specification provided on Canvas. Very simple equation. What will happen is you'll do this sand reading divided by clay reading times 100, and if you get 95, or you'll get like 95.6, and that means that your sand is 95.6% not clay. So it's pretty clean. If you get a reading that's like 70%, that means you got 30% clay in that sample, which is probably not good for your for what you're doing. You want the cleaner the sand or cleaner the fine aggregate, the better. And then this is our video for sand equivalency.
For ASHTO T176, which determines our sand equivalent value of our fines, the equipment needed is, we'll need our sand equivalent solution, which is calcium chloride. We'll need our graduated cylinder for our sand equivalent tests, our calibrated weighted foot, a scale, a stopper for our graduated cylinder, and we'll need a mechanism to be able to shake our sample. What you see here is a mechanical shaker that is made specifically for a sand equivalent test. If you do not happen to have a mechanical shaker, you can actually shake it by hand, and I will show you how to do that in this process. So when we first start the test, we have to have our graduated cylinder. We need to add some solution to this cylinder. And our graduated cylinders are in inches. They go to 15 inches, and we'll want to add 4 inches of solution to the cylinder. The amount of sample needed for a sand equivalent test is that it takes an 85 millimeter tin. This is an 85 millimeter tin, and you can buy them at most any place that sells asphalt testing supplies. I have my sample here, and you just add it by hand. Also like to tap on the bottom of the tin to make sure it is completely full. And once we have a full cylinder, a full tin, we will add this sample into our graduated cylinder. And if you have a small funnel, that helps with this process. I have added my sample to the graduated cylinder. Now I want to place the stopper on. I take it, bump the bottom, shake it just a little bit, because what we're wanting to do is we're wanting to get this solution to mix with our sand. Once it is mixed, now we want to let our solution and sample set for 10 minutes before we actually shake the sample. So I'll set my timer. And then we'll come back in 10 minutes. So once 10 minutes is up, we'll stop our timer, and now we have to shake our sample. We have a mechanical shaker here, and if your lab has one, they are very nice to have. I will put this sample and shake it in our mechanical shaker, but I want to show you, if you do not have one, you can't shake it by hand. And the way you shake it by hand, the specification calls it a throw. And a throw has to be 9 inches in length. I've been in labs before where you'll walk up to a counter, they'll have a mark here on the counter and a mark a little ways down from it. I've even seen tape used. If you take a tape measure out, it'll probably be 9 inches. That's where they run their sand equivalents. So if you take 9 inches, and it's pretty much about like this. So you determine where that 9 inches is, and you have to do 100 throws in 60 seconds. So you have to be moving pretty good to be able to shake this by hand. Since we have a mechanical shaker, I'm going to place it in it and let that do the work for us. These graduated cylinders have a hole in the bottom because they are designed to fit in these shakers. And so, place it there, roll back, hit start. The mechanical shaker runs for 45 seconds. So after 45 seconds, it will stop. Take our cylinder sample out, we'll place it on the counter. And now we have to fill our cylinder with our solution. If you have material that's on a stopper, try to get it back in the cylinder if possible. And now We want to make sure our sample is at the bottom, and I will add more solution. I like to get it off the sides, but as you're filling your cylinder up, you want to take your wand, this is called a wand, and continue to stir and jab at your sample. And we'll fill our cylinder up to 15 inches with the solution. You want to try to keep your wand in your sample as it is filling up. You don't want to take your wand out and just let it fill up. You want to keep your wand down in your sample and continuously fill. You kind of have to try to time it a little bit to get it to hit right at the 15-inch mark. Once our graduated cylinder is filled to the 15-inch mark, we now have to let our sample sit for 20 minutes. After 20 minutes, we can then take our 2 readings that are needed. After 20 minutes is up, we can now take our clay reading and our sand reading. Those are the 2 readings that are needed to determine our sand equivalent value. The first reading we want to take, as you can see our sample is separated out, we want to take our clay reading first. The clay reading will be the material that is on top here. The second reading we'll take is our sand reading, and we'll also need to use our weighted foot to determine our sand reading. So for this sample here, our clay reading would be, we're 4 inches. This is in 1/10 of an inch increments. So 4, 1, 2, 3, 4. So our clay reading for this sample would be 4.4. Now for this sample, you can tell where the sand level might be. And you may can read it and say, well, my sand will be 4.2. We want to use this weighted foot because we can't tell with every sample, and sometimes it's hard to see where the sand actually starts. Sometimes that clay will be meshed in with our sand. And the way we determine our sand reading is with our weighted foot. We'll just take our weighted foot, we'll place it down into the sample, and it will rest on the sand itself, so we'll know exactly where our sand reading is. The only problem is when I stick this weighted foot in my sample, when I hit that clay layer, the clay is going to disperse and we won't be able to see the reading. That's why these weighted foots come with a marker on them. We'll actually read where the marker states. And these markers are placed exactly 10 inch from the bottom of our weighted foot. When we place the weighted foot in, you want to be careful and not bang on the sides of the cylinder because you do not want to compact your sample down any. So you want to just ease it down into the cylinder. And we see our clay disperse, so it's hard to see where the bottom of our foot is, but we know it is resting on top of the sand. And since we cannot tell where the bottom of our foot is here, we can read where our marker reads. And for this example, our marker is at 14.1. So our sand reading would be 14.1 minus the 10, because that's the distance from our marker to our bottom of our weighted foot. So our sand reading would actually be 4.1. And then to determine your sand equivalent value, you just take your sand reading, divide it by your clay reading, and multiply times 100. And typically when we run a sand equivalent test, you want to take 3 tests and do 3 separate runs and average those to get your result. And also, sand equivalent is rounded to the whole number. You do not follow normal rounding practices when it comes to sand equivalent. Sand equivalent is one where you always would round up. So if the average of our 3 runs was a 45.2, we would still call the sand equivalent value for this material a 46.
So very simple test again. Kind of takes a little bit of time because you got to wait it out, but it's easy enough to do. That kind of ends our aggregate lab videos for doing the actual test. So if there's any questions, you can ask me. I just want to go over a few, like probably frequently asked questions that y'all might have. The aggregate data will be posted Wednesday evening. The aggregate report is due Friday, July 3rd, so that's in quite a while, like 3 weeks from now, at 5 p.m., same as the steel one. Steel is due at 5 p.m. this Friday, so don't forget that. Also, it is a long report because there's so many tests. The length of it is because there's 9 tests. You have to describe all 9 tests and go through methodology, and then results. You have to provide results for pretty much all the tests. And then also, I'm going to upload this recording to Canvas, and I'm going to upload each of the test videos on their own, so that if you wanted to go watch how you do fine aggregate specific gravity, you can go watch that video and see how that's done without having to sift through a Zoom meeting. But if you wanted to go back and listen to me explain some of these details during the slides, you can also go listen to that as well. So that's hopefully Canvas will allow enough space for that. I think there's a limit to it, but I will try and do my best to see what I can do about getting that into each of the folders for that. So that concludes testing. And give me 1 second.